I have reproduced part of the table right up here to remind you. These elements are too far from the noble gases to lose or gain electrons to reach one of the noble gas electron configurations. It's just energetically not feasible. So other things become determining then. And I'm going to use tin as an example because it's an easy one to appreciate. It forms two ions. It forms tin 4+ in compounds like SnO2, and it forms tin 2+ in compounds like SnCl2 or SnF2. If you remember the original Crest toothpaste with stannous fluoride, that's SnF2, and there's SnF2 is a good source of fluoride ions to fluorinate your enamel, to make it more resistant to whatever you expose it to. So here's tin right here in group 4A. It's under carbon, a few steps down, and it can't lose enough electrons to make it all the way over to the next noble gas this way, or can't gain enough to go, can't gain enough to go this way or lose enough to go that way. So it does something different. The tin 4+ ion starts with tin. The valence configuration now, if you look at the periodic table, which I hope you're doing, 5s2, 4d10, 5p2 for tin. Okay? Tin is in group 4A, so it's an S2P2, and in this case, it's an S2P2, and it has a filled 4d10, 4d subshell there. So if it's going to lose 4 electrons, it should be clear that they're going to come from the 5s and the 5p. And so tin 4+ has a krypton configuration plus 4d10. And here are the 4 electrons that are taken away from it. Now this is a special kind of an electron configuration that is stable for elements in this region of the periodic table. And because of the fact that this is 4d10, krypton has 4s2, 4p6. So 4s2, 4p6, 4d10, that's a filled n is equal to 4 shell. And there isn't any noble gas exactly like that because of the arrangement of the periodic table. So this is called a pseudo noble gas configuration. A noble gas plus the next D subshell filled here. Krypton 4d10. So that's part of what makes tin 4+ a stable ion. Now in tin 2+, it's a different situation because you're taking away only 2 electrons. And we should expect the highest electrons in the electron configuration of tin to be lost first, right? We're going to take off the top. All right? So in this case, we have 5p2. That's how many electrons we need to remove. So when we do tin 2+, we're going to remove the p electrons, and that's going to leave us with, again, krypton and 4d10, but in between is 5s2. Okay? Now that 5s2 is given a special significance for these elements. It's called an inert pair. An inert pair. And the reason for that is it has an unexpectedly high ionization energy. You don't have to worry about what the ionization energy is, but the stability of this pair of electrons makes the tin 2+ ionic state more stable than it would be otherwise. So you can apply that to all of the elements that are here. In the group 3A, we would lose these. This would be an S2P1 configuration with a filled D subshell for all of these. So we would lose the P for group 3A's, gallium, indium, thallium. We lose the P1 first, and that would give us an M1+, gallium 1+, indium 1+, thallium 1+. And that would be analogous to tin 2+. It would be an inert, these would be inert pair configurations. Now in the 4A here, it's just like tin 2+, tin 4 plus, lead has the same thing right under it, lead 2 plus, lead 4 plus. Bismuth is on the edge of things here. It has a 3 plus and what looks like a 5 plus, but it's probably really not. So my advice to you is when you have to write down the ions for these elements, look at whether they're in 3A or 4A, because I don't think we ask you the 5A one anywhere. And imagine first that you remove the p electrons. If you remove the one p electron, which is all these elements have, then you get M with a single positive charge and an inert pair, S2. And if you do that in 4A, then you take away 2 p electrons, and that leaves, again, an inert pair configuration. If you look at the maximum number of positive charges, there'll be 3 for the group 3A ones because they will remove the P and both S's. So that'll give you 3 plus here. So gallium 3 plus, indium 3 plus, thallium 3 plus. This is exactly analogous to tin 4 plus and tin 2 plus. Okay. Now to write the electron, were there questions on that last slide? Sorry, meant to ask. Yes?
Are the terms inert pair and pseudonoble gas then used respectively for each group?
For the elements in this region of the table, the ones that have a pair of valence s electrons are called the inert pair. That's an inert pair configuration, quote unquote. The ones that have a filled d subshell but no outer s or p, that's called a pseudo-noble gas configuration. And that applies here too. Other questions on this? All right, good. So we have a problem here. Write reactions with electron configurations to show the formation of the common ions of these 3, iodine, strontium, and thallium. Okay? Now, iodine we've done so many times, that should be pretty easy. Remember, 6A and 7A form anions with the same number of electrons as the nearest noble gas. So iodine is 1 electron short of the nearest noble gas, and so it's going to be an easy one to do. Strontium is in group 2A, so it's going to lose 2 electrons to go to the nearest noble gas, right? They're going to go down the drain and form a 2 plus for it. Thallium is in group 3A, and it will lose either its outermost p electrons or its outermost s and p electrons. So let's look at what we have. Iodine, here is 5s2, 4d10, 5p5. It's 1 step away from the xenon configuration, so we expect it to add 1 electron, go to I minus, and I minus has the xenon configuration. Questions on that one? Okay. Strontium is down here in group 2A. It's going to lose 2 electrons to get back to the krypton configuration. 2 steps. 1 step to 37, 1 step to 36 from 37, and we will have strontium 2 plus. And of course, we've already expected that from group 2A elements before, but it's the stability of the krypton configuration that drives it. Thallium is down here right under indium. It's in 3A, so its outermost electron configuration is S2, P1. All right, so it could lose 3 electrons to go to a pseudo-noble gas configuration, or it could lose 1 electron to go to an inert pair configuration. This is the latter. Thallium goes to thallium plus an electron. This is S2, 6s2, 5d10, and inert pair configuration. And if both the 6p and the 6s electrons go, a total of 3, then we'll get thallium 3 plus. So that's how we predict the magnitude of the charge for these elements. Questions? Okay. Now I want to talk a little bit more about the transition elements, because we mentioned before that their ions are pretty much unpredictable. The generalizations that you can make about these elements are that most of them have a +2 state and a +3 state, and some of them have some additional states. But that's the most common thing, a +2 and a +3. Now, experimentally, when that happens, when you form an ion from a transition metal, the chances are very high that that ion is going to have one or more unpaired electrons because of the factors that we've described so far. Transition metal ions rarely attain a noble gas configuration. Now, usually what we're dealing with in the case of a transition metal is some number of s electrons, which we call ns. This could be 4s, and some number of d electrons. This would be 3d, for example, in the first transition series. 4s, 3d. So we call it n-1d means 3. Okay, now it could be 5s and 4d, or 6s and 5d. All right, so what happens? When these elements form ions, they almost always, with few exceptions, lose at least 2 electrons to form M2+. And those 2 electrons that come out are the s electrons. The s electrons are lost first. There is more credit not earned in midterm 3 because of this problem than any other factor. For some reason, half the people in this room are going to forget that the s electrons go first. And 75% of those that aren't in this room will forget because they never heard it. Okay? So memorize that. The s electrons come out first, and then you start taking the d electrons. So what I want to do is to talk about what's left after you take out the 2 s electrons and 1 or 2 d electrons. All right? Usually, with a few exceptions, you end up with some d electrons left. These d electrons are unpaired in most cases. Some of them, at least, will be unpaired. If they're unpaired, that makes the compound, which they're part of, paramagnetic. And experimentally, what that means is that they will have magnetic properties that are different from ferromagnetism, like an iron magnet. But nonetheless, they have certain qualities that parallel ferromagnetism. Here's what I mean. If we took one of these compounds, like let's suppose we put in here iron sulfate, iron 3 sulfate. If we put it in this little container right here, a little bit later we'll show that iron 3 has a lot of unpaired electrons, a bunch of them. Now, each one of those little unpaired electrons, each one acts as if it was a little bar magnet. And in the case of ferromagnetism, the structure of the material is such that those little bar magnets all feel the presence of each other, and they all line up in a way which is beyond the scope of our course to explain at this point. But that's in ferromagnetism. In paramagnetism, each little bar magnet acts independently. However, if we put a sample of a paramagnetic material, like an iron 3 salt, into a little container here, and we set up a balance so that an equal mass is on this side and no magnet is here, so the balance is just balanced with the weight of that material, and then we bring along a magnet, this stuff will be attracted to the magnet. And what happens will be what you see here. The apparent mass of that material, as far as the balance is concerned, goes up because, in fact, it's attracted to this magnetic field. So these magnetic properties, its apparent mass increase when we put the magnet there, can be translated through some pretty sticky mathematics. Take my senior course and we'll go through it, into the number of unpaired electrons. So atoms, ions, or even molecules with any unpaired electrons are attracted to a magnetic field, and they are said to be paramagnetic substances if they have any unpaired electrons. Okay. Now, do we have questions on this concept of what a paramagnetic substance is? All it has to have is one unpaired electron, one or more, and it's paramagnetic, and it will be attracted to a magnetic field. All right? Now, paramagnetism, therefore, can be defined as the attraction of species with unpaired electrons to a magnetic field, and the magnitude of that attraction will tell the informed person how many unpaired electrons are there. If we take silver, for example, in the periodic table, silver lies right under copper. Its electron configuration in the valence parallels that of copper, as we've said several times before. Unexpectedly, it's 5s1, 4d10, whereas we might have expected it to be 5s2, 4d9. It's not that. It's got one unpaired electron in the s subshell, and therefore silver atoms are paramagnetic. And this can be shown by a beam of silver atoms striking a magnetic field. Now, on the other hand, if you have an atom or an ion or a molecule which has all electrons paired, it's called diamagnetic. And diamagnetism is the absence of unpaired electrons. No unpaired electrons there. And the difference is if you put a diamagnetic substance like sugar into that balance that we saw in the previous slide, and you balance it all out perfectly, and then you bring a magnetic field, all of a sudden it seems like the mass of the sample got less by a little bit. And that's what happens when you have a diamagnetic material. So we need to know about electron configurations to see whether they're paramagnetic or diamagnetic. I'm going to start with cadmium here. And cadmium is under zinc in the periodic table. So its electron configuration is S2D10, in this case 5s2, 4d10. Cadmium is right here, right under zinc. Okay. So if we form cadmium, if we formed cadmium 2+, what would be the electron configuration in the valence for cadmium 2+? He says 4d10. Do you agree? I agree with him. The s electrons come out first. So this is 4d10. Is it diamagnetic or paramagnetic? It is diamagnetic. There are no unpaired electrons because the only valence electrons are those in the 4d10, and that would mean all 5 d orbitals had a pair of electrons in and no unpaired. Everybody comfortable with that idea? All right, good. Let's talk about iron then. I told you I was going to show you iron 3. Iron atom. Iron atom is 4s2, 3d6. We learned that last week. If you remove 3 electrons from 4s2, 3d6, where does the first electron come out? You said the 4s. Good. Excellent. Wonderful. Don't forget. Comes out of the 4s. The second one comes out of the 4s until the 4s's are gone. Where does the third one come out of? What's left? It's got to come out of the 3d. So that makes iron 3 plus, argon, 3d5. The s electrons are gone, and one of the d electrons are gone. What's the box diagram look like? Well, here's iron, 4s2, 3d6, 4 unpaired electrons. The box diagram is what you use to visualize how many unpaired electrons there are. If you go to iron 3 plus, the 4s is empty, as we predicted that it should be. The 3d has 5 electrons with parallel spins, and that means a very stable configuration, but highly paramagnetic. 5 unpaired electrons. Okay. Let's look at these ions, copper plus and zinc 2 plus. Yes, go ahead.
So it's have 5 valence electrons, correct?
What does?
Iron 3 plus?
Iron 3 plus, yeah, should have, iron has 8. We took away 3, that would be 5. Other questions? Okay. Copper plus and zinc 2 plus have respectively 1 s electron and 2 s electrons in their valences. So copper is 4s1 3d10, and copper plus, I mean the parent atoms have 1 and 2. So copper 1 plus would lose this 4s electron, and it would be 3d10. Zinc starts with 2 electrons, 4s2. It loses them to get the same electron configuration as copper plus. So we say zinc 2 plus and copper plus are isoelectronic. They have the same number of electrons. And they are both diamagnetic because they're D10 configurations. D10. And here it is in a box diagram. You could see you would not expect this to be attracted to a magnetic field, either one of them. Okay.
What if it's like 3D9, would it be paramagnetic or diamagnetic?
He asked if it turned out to be 3D9, would it be paramagnetic or diamagnetic? What do you think? It's going to be paramagnetic, right? Because there's going to be one d orbital that has only 1 electron in it, and that one, therefore, is unpaired. So a D9 configuration would be a paramagnetic configuration. Okay. Writing electron configuration, predicting magnetic behavior of transition metal ions. Okay. Write equations with the electron configuration of formation of metal ions below. Predict if the ion is paramagnetic. How come we have so much talking? If you have a question, I'll be glad to address it. Thank you. Cobalt 2 plus. I would like for you to write down the valence electron configuration of cobalt right here, and I'm going to show you the periodic table. Here's cobalt. So I would like for you to write down the valence electron configuration of cobalt atom on your paper. Sorry, this isn't as bright as I would like it, but it is element 27, and if you can't see well enough to count, it's 1, 2, 3, 4, 5, 6, 7 atoms over in the transition element. Write down its valence electron configuration on the paper. Okay. You got it? Somebody want to tell me what it is? Tell me. Who wants? Raise your hand. Yes, go ahead. Plus 2 electrons. So this is for cobalt atom, not cobalt 2 plus. Cobalt atom. Excellent. 4s2, 3d7. Let me write down what she said. Cobalt atom, 4s2, 3d7. Okay? Now, we're going to form cobalt 2 plus here. We're going to have cobalt 2 plus, and over here somewhere are the 2 electrons that came out that you just mentioned. So, now I want you to write down what the electron configuration of cobalt 2 plus is right here. It's 2, 3d7, minus 2 electrons. So what's cobalt 2 plus? Who wants to tell me? Yes? 3d7, she says, and I agree with her. The S2 come out before the D. Okay? Now, predict if this ion is paramagnetic. Draw the box diagram. Draw the box diagram on your paper for 3d7. Have you got it? How many unpaired electrons? 3 unpaired electrons. Let's see what I get. 3d7. 1, 2, 3, 4, 5, 6, 7. You're all right. 3 unpaired electrons. So it's paramagnetic, right? Good work. Good work. Questions on that one? Well, let's do this next one. What's the, write down on your paper the valence electron configuration of chromium atom. Chromium atom is a special one. Maybe you'll remember it. Here's chromium. Z is equal to 24 right there. So write down its electron configuration, its valence electron configuration. This time I want to ask somebody else. Okay, chromium. What's the valence electron configuration? For S1, 3D5. I agree. It's a special case, remember. Now we're going to go to chromium 3+. Where does the first electron come from? It comes out of the 4s. Okay? So that leaves 2 electrons to be removed from the 3D. The 3D had 5, and it's going to lose 2, so what is its electron configuration? 3D3. 3D3. Okay? Is it paramagnetic or diamagnetic? Draw the box diagram. Don't leave anything to chance. It's an awful lot of credit lost for lack of correct electron configuration in the third midterm. 3D3, easy. There it is. 3 unpaired electrons, and it too is paramagnetic.